Hello everybody, so I'm from the Stability and Performance team, so just continuing the work started last week, the water surface stability. So because of the time constraints, as most of the sub-teams, we just divided the different responsibilities, which is provisional with regard to the work. We do have some overlapping sections, so here's the way we split the work. The different sections. So I'm taking care of everything that's taking place on the water surface. So as we said last time, so the water surface is basically divided into two parts, the static and dynamic stabilities, basically the floating after landing and before takeoff, as well as the takeoff and landing stabilities. So the floating condition basically would be probably in the loitering phase, but I'm not very sure about that, but I'm going to submerge the wings. So yeah, and then the proposing, which I started last week. So with regard to the mission segment and the design proposal, we're looking at an amphibian type of seaplane defined by a hull type of fuselage, and a retractable landing gear to be able to land and take off from land as well. Something like that with the different parts labeled. In the design process, the stability considerations we have to give to the different operations taking place in water. So at low speeds, in the absence of very little aerodynamic forces. So we are looking at the longitudinal and transverse stabilities at all the different speeds, and we have to use water rudders, which are frequently used in design. So basically that's from the research we've done. And the water control will be assisted in addition to the rudders by positioning the tail rudder probably in the top wash, but that's not very sure because it's not like a subject of debate so far. And the high-speed operations and takeoff and landing on water should be controllable at all speeds with the help of the control surfaces, essentially. So on the sea, we have different type of sea conditions to account for when we are going to study the different stability phases. According to the DARPA specs, in the loitering phase, we'll have to take a sea level 5, which is basically a rough kind of condition. In the risk of capsizing, when we are simply floating at the surface of water, all depends on the height to length ratio, which is a ratio of the amplitude to the wavelength, basically of the waves. So in our case, we have something like 200 meters of wavelength, if I'm not mistaken, with an amplitude of 2.5 meters. So that will give us an idea of how high is our risk of capsizing. So the lower that ratio gets, the higher the risk is of capsizing during floating. So the hydrostatic stability part is overlapping with my teammate part, and consists in two different parts, which are the longitudinal stability and the transverse stability, which was presented last week, I guess. So in the longitudinal stability, we care about the position of the metacenter with respect to the center of gravity longitudinally, along the longitudinal axis. Whereas in the transverse stability, we care about the same position and about the restoring moment the center of buoyancy will give following a disturbance. Some criteria we found with regard to the transverse and longitudinal metacentric height. So those are some mathematical equations we found, some criteria that have to be verified, and that will be used for further Excel or MATLAB computations, following the dimensions we get from the other addition to porpoising, which have been mentioned last week, there are two other dynamic instability occurring at the surface of water, essentially skipping and battering. Depending on skipping, for instance, depends on the speed we are approaching and the position of the nose relative to the horizontal. But that's much less of a worry because generally skipping leads to a decaying oscillation. Contrary to what's going on usually with porpoising, which keeps on amplifying if nothing is done. Essentially, if no damping is done, but we'll come back to that later on. And battering is just an SPPO. So we care more about what's going on in porpoising, which seem to be the industry concerned about stability issues. So, as we introduced last week, so it's just a pitch and heave coupling with growing amplitudes that can lead to several problems with takeoff and landing equally. There are many different ways we've found how to model and deal with porpoising. So the forces acting on a prismatic hull, the analysis very often confines the diagram of forces to what's going on the surface at the hull, instead of accounting for the whole body. So for one given rise angle, the onset of porpoising is essentially determined by the trim angle, which is the angle between the level of water, assumed horizontal, and the bottom of the hull. So the one general rule used by this guy called Savitsky, which has done a lot of work on this subject, is to lower the trim angle to avoid the porpoising. And on this graph we can also see how trim angle varies with the lift coefficient, and how by defining a dead rise angle for our hull, we can define a regime of porpoising and therefore determine what our stability limits are with respect to porpoising. The Savitsky approach is something that other research frequently refer to, but its limitations are that it's valid at low Froude numbers, which essentially translate into low speeds. And it's limited to the hull analysis. As I said, it's just accounting for forces that are acting on the hull. And if we compare what's going on, the behavior, because in the end we will look to optimize we're looking for a kind of optimization of the trim angle as to minimize the drag in water. So the variation of resistance with the displacement Froude number, basically the speed, you have a departure beyond a certain speed which occurs between a planing boat and a hydroplane, which sets somehow the limitation. So validity of the Savitsky approach is for low Froude numbers. So porpoising has been the equations of motion, the state space system, has been described by some research work. But the problem is, as the speed rises, which will be the case for us when we take off, you have there's a lot of non-linearity going on with the restoring coefficients, inertia coefficients in one of the terms, and this, namely, the porpoising is initiated when two of those coefficients get opposite signs. So any attempt to try to linearize those equations will give a very inaccurate reflection of what goes on in actual reality. So there's a lot of dependence on empirical work in the design in order to minimize the porpoising effect. So damping is one of the ways that's being used in order to attenuate porpoising. So on this diagram, we see how the values of two of those of the restoring coefficient explain how porpoising occurs when we take negative opposite signs beyond a certain Froude number, which here is around 0.6. So damping can be roll damping and heave damping. There are some equations that describe these. I'll put them here, that we'll use later on in Excel sheets. So a rule of thumb would be to flatten the aft part of the forebody to 1.5 times the width of the hull. And in terms of directional stability, keel and 60 keelsons tend to keep the craft in a straight line direction, and large vertical tail on the other side can be used to attenuate the water looping effect due to a long forebody. But the idea again is whether to position in the prop wash or not. The use of auxiliary floats has been mentioned last week. Now just come up with some kind of equation to explain how the use of tip float will restore the moment following a disturbance. So the next steps will be to work out, to optimize basically many of the variables we have, how to work out the control, the trim devices, and get some numbers using approximations instead of numerical techniques to differential equations. So that's some of the efforts that have been used. Thank you very much.
So can I start with the kind of, you had a number of empirical equations,
yes,
which have various parameters in them, so I was trying to read.
Yeah.
Do you foresee any difficulties with estimating what these parameters are? If you want to use these for?
Well, this one is basically the most difficult one, which is the purely empirical one, because of the non-linearity and this kind of thing occurring as we increase the speed. But
so are you
the industry... Sorry.
Okay. I wasn't asking about this first, but I'll ask that now. Go back. No, sorry, to the non-linear equation.
Oh, this one?
Yeah, so are you saying that if I so you pick a speed, now I linearize the equation, are you saying this is always linearly stable?
It's difficult to conclude about the porpoising stability beyond a certain speed, actually, because you have a lot of non-linear effects taking place with two of the inertia coefficients. And beyond, for example, here at 0.6, we cannot linearize. I mean,
you can linearize if you want to.
But that would be a very false representation of what goes on in the reality.
Isn't it normally the case with things like this that, okay, you've got very non-linear behavior, but the linear part becoming unstable indicates some change in behavior? Or is that not the case?
Well, so far, like, what I've found in like 2 different research papers, that linearizing is giving false conclusions, basically.
Okay, so what's your plan?
Use approximations. The approximation that the industry is using. One of these rule of thumbs, and some there are many approximations that are approximated equations that we're going to plug in the Excel or MATLAB file and use this, because those equations have been built up like from empirical data, basically.
So you've got this non-linear behavior. If your design was such that porpoising did not occur, would you enter the non-linear regime?
I think it will all depend on the... I mean, to conclude that porpoising is not occurring, it's like a permutation we're going in, right? You first have to know at what speed you're going. I mean, it all works with the Froude number, I guess. And from there, you know approximately if you're entering the nonlinear regime and whether a linearization can give some kind of accurate prediction of stability. But I think you've got to know the speed, the Froude number you're working with first. This is generally how we do it, and then compare with what they get empirically.
Can you go back a couple of slides to where you were showing stable and unstable and porpoising crash?
This one?
Further back. One more. Ah.
Yeah.
So here what we're seeing is that
It's the variation of the trim angle with the lift coefficient. So we have different dead rise angle for the hull. So this line, this graph basically, which is drawn empirically, and which you can use, which is like a benchmark data you can use to determine basically whether you fall into those kind of this limit or hit on this side. So starting from something from one dead rise angle, which we are expecting.
Does this apply to hulls that have an afterbody, however? So you have something extending aft of your center of gravity. Would that still apply to that?
Well, in the limitations I've found for the Savitsky, so the criticism has been mainly about the absence of tail, and the risk of extrapolating the Savitsky approach beyond certain Froude numbers as well. It's, yeah, those kind of things. But yeah, this is something I have to check.
I would suggest you look at this versus some tank test data for similar seaplanes with tails, with afterbodies, as well as damping coming from an aerodynamic surface.
Okay.
And you will see that it might make a bit of difference.
Okay. This one accounts for this approach. Well, that has to be approximated. Accounts for a tail in this one. Those guys have worked on that. That's quite recent one. The Savitsky one is like 1964, and this one's like 2000 something.
It's inertial to gravitation.
Any more questions?
The model you just described, if I understood correctly, you said that it's only based on hydrodynamic forces, right? Like it doesn't
no.
consider any aerodynamics of the not
This one?
submerged part. Yeah.
Yes, well, it's considering the hydrodynamic forces, like as well as the lift forces that's on the wing.
Coming from which side?
I mean, any upward forces acting on the wing are accounted in the, because I think on the, well, this is like a racing boat model basically, and they have lifting devices as well.
Okay, so that CL that goes in the graph is the lift coefficient associated with the bottom of the hull, basically.
It's the with
Refers
the
to water,
lifting, with
right?
the lifting
Hydrodynamics.
surfaces. The hydrodynamics one is the one that giving the upthrust every time it sinks, basically displacing a volume and giving the upthrust.
So do you guys already have estimates? So at the maximum speed, the maximum speed I guess on water would be the takeoff speed, right?
Yes.
So in that condition, can you make a statement that, for example, the total drag, like so that we can forget about the air when we are on water, or maybe nothing?
If I'm not mistaken, the research paper talks about something like that, but I'm not very sure. Like I've worked only with stability issues, but I think there's a kind of critical speed where this happens.
I mean, something to check, I guess. Right?
Yes.
Is there anything for sailboats?
Sailboats.
Porpoising or whatever it's called for sailboats? Any research?
No, to be honest, no.
I don't think you're going to go fast enough for
No?
that.
Okay.
And I guess the speed is lower, so flight number will be lower. So prediction for stability will be easier, I guess.
All right. Okay.